Hello and welcome to today's class. Today we're going to be looking at Bernoulli's equation. Bernoulli's equation can be used to describe the flow through a pipe, through a fluid through a pipe, by considering the changes in pressure, the changes in velocity, and the changes in height. Essentially, it's conservation of energy. So we'll consider each of those things and we'll look at them, the energy which is generated by each of those things existing in the fluid, and we can use that to predict how the fluid will change as it flows through the pipe. We'll use that in conjunction with conservation of mass, this idea that a fluid, if it's flowing past a certain point, if that point is narrower, the fluid must be flowing faster for the same volume, same mass of fluid to be flowing at a certain time. And if that section of pipe is wider, then obviously the fluid will be flowing slower. So we get the same conservation, the same quantity of fluid flowing through that pipe at that time. Okay, so we'll have a look at Bernoulli's equation. We'll have a look at some applications of that when our pipe changes height, when our pipe changes cross section, and then we'll have a look at some examples on that. Okay, so today's class, all about Bernoulli's equation. Okay, so when we're considering fluid flowing through a pipe, we need to consider the energy associated with that fluid inside that pipe. Essentially, we can consider three types of energy associated with that fluid. We can consider the energy associated with the pressure. So we've got pressure, energy, and that's equal to PV, pressure times by the volume of the fluid. We've then got kinetic energy, and that's equal to a half m u squared, half mass times by velocity squared. And then we've got our potential energy, and that's equal to mgh, or mgz. Let's use z for height in this case. Okay, so we've got the energy associated with the pressure, the energy associated with the movement of the fluid, the kinetic energy, and the energy associated with the height of the fluid, the potential energy. Now, we know from conservation of energy that this cannot be destroyed or created. Energy can't be destroyed or created. So let's make a few assumptions. Let's assume that our fluid is flowing through our pipe. It's steady flow, it's streamlined flow, the density is constant. So we're not worrying about things like compressibility. We're not worrying about energy losses associated with friction at the edges of the pipe, or any change in heat, any losses associated with that due to heat transfer. Okay, if we simply consider these three energy sources and the fact that they're constant, then that will enable us to work out, to calculate how the fluid changes as it flows through our pipe. Essentially, what we're saying is that PV plus a half u squared plus mgz equals a constant. It doesn't change. Okay, now we know density equals mass over volume, so therefore volume equals mass over density, or the inverse of our volume equals our density over our mass. Okay, so if we take that relationship and we stick that into this equation here, then we can simplify it. Okay, so let's multiply through by 1 over E. So we've got our pressure plus half multiplied through by rho rho u squared and divided through by m. Do the same thing here. We multiply through by rho, so rho g z and divided through by m, and that is a constant. Okay, and that's what Bernoulli's equation tells us. The pressure plus a half rho u squared plus rho gz equals a constant. Okay, or if we're considering fluid flowing through a pipe, if we consider the pressure at position 1 and a half rho u1 squared plus rho gz1. So that's the energy associated with the pressure at position 1, the kinetic energy at position 1, and the potential energy at position 1. That's equal to the same three sources of energy at position 2. So P2 plus a half rho U2 squared plus rho GZ2. Okay, so that energy at position 1 is the same as the energy at position 2. So generally we will assume that there is zero energy losses from position 1 to position 2 when we're considering the transfer of fluid from one position to the next. However, we can actually use Bernoulli's equation to quantify the magnitude of those energy losses. If we have energy losses, if we're interested in, let's say, friction losses through fluid flowing through a pipe or something like that, we can say, well, the difference in energy must be due to those energy losses. So we just said P1 plus a half rho U1 squared plus rho GZ1 was equal to P2 plus a half rho U2 squared plus rho GZ2. Okay, so the energy at position 1 is the same as the energy at position 2. That's assuming zero energy losses. Okay, but if we are interested in the magnitude of those energy losses, actually the energy at position 1 is clearly going to be the same as the energy at position 2. We put plus our energy losses on the end here. That would also be true. Okay, so now we are considering that there is some loss of energy. So let's say, for example, we were looking at the friction of a pipe and we were interested in the I don't know, the surface coating or something like that, and we were looking at fluid flow through that pipe. We could consider the energy at position 1, the energy at position 2, and then any difference must be associated with those energy losses. So we could try different surface coatings, and therefore we could start to quantify the magnitude of those energy losses. Okay, so let's consider this first situation. We've got fluid flowing down a pipe. We've got a convergent tube. We're going from a large area, cross-sectional area, to a small cross-sectional area. Let's think about what's happening to the velocities and the pressures as we go through this pipe. Now, if we assume this pipe is horizontal, Z1 is equal to Z2, so we can neglect one of our terms. That simplifies things. So there's Bernoulli's equation as we've written it up until now. Our pressure plus our kinetic energy plus our potential energy is equal to our pressure and our kinetic energy and our potential energy at position 2. This is position 1, this is position 2. Okay, now if Z1 is equal to Z2, this term here cancels with this term here. Okay, so we simplify it to this. Our pressure and our kinetic energy at position 1 is equal to our pressure and our kinetic energy at position 2. Okay, now we know from conservation of mass that our velocity times by our area at position 1 is equal to our velocity times by our area at position 2. Okay, now area 1 is clearly bigger than area 2. Okay, so if area 1 is bigger than area 2, velocity at 2 must be bigger than the velocity at 1. Okay, so we've got an increase in kinetic energy. Velocity at 2 is bigger than the velocity at 1. Okay, so a half rho u2 squared is greater than a half rho u1 squared. Okay, so this term here is bigger than this term here. If the overall terms are the same, the overall size are the same, this is increasing, this must be decreasing. So P1 is greater than P2. P1 is greater than P2. So we see a decrease in the static pressure. Okay, and that's represented by these fluid taps. We've got these taps in here. We can see the height of our fluid. Pressure equals rho GH, so the height of this fluid is clearly related to the pressure inside of the pipe. Okay, and we can see the height of the fluid here is much greater than the height of the fluid here. So we're seeing a decrease in pressure. That's what we'd expect. So as our fluid flows from left to right, it's increasing in velocity. Kinetic energy is going up due to conservation of mass. Kinetic energy is going up, and due to Bernoulli's equation, if the kinetic energy is going up, the energy associated with the pressure must be going down, so our pressure is decreasing. Our potential energy is the same, and the center of this pipe is horizontal. So we've got an increase in kinetic energy, we've got a decrease in pressure. Okay. So let's now consider this next example. Again, we've got fluid flowing from left to right. This time we haven't got a convergent pipe, we've got a pipe which is changing height. Okay, so we've got P1, U1, A1, Z1 rho in position 1, and we've got P2, U2, A2, Z2 rho at position 2. Okay, notice we're assuming that rho is the same between 1 and 2. Okay, we haven't got any compressibility, our fluid density is not changing. A1 is clearly the same as A2. Okay, so conservation of mass tells us if A1 is the same as A2, that U1 must be the same as U2. U1 is the same as U2. Okay, so let's now consider Bernoulli's equation. We've got our pressure, we've got our kinetic energy, we've got our potential energy. Pressure, kinetic energy, potential energy. Now, if U1 is the same as U2, half rho U1 squared is clearly the same as half rho U2 squared. So those two will cancel each other out. So we can neglect those terms. So that simplifies Bernoulli to this. P1 rho G Z1 is equal to P2 rho G Z2. Now, clearly rho G Z2 is greater than rho G Z1. Okay, Z2 is greater than Z1. We've increased in height. Okay, we're gaining potential energy. So if this term is going up, this term must be going down for it to remain equal. Okay, so P1 is greater than P2. We've got a decrease in static pressure. Okay, and again, you can see that with the pressure taps into the side of our pipe. We've got a certain pressure here, and kinetic energy is staying the same, but our potential energy is increasing. If our potential energy is increasing, then the energy associated with the pressure must be decreasing. So therefore, our pressure is decreasing. So we've got a high pressure here, and we've got a lower pressure in position 2. So let's now consider some of the limitations of Bernoulli. The main approximations for Bernoulli was that friction was 0, the flow was streamlined, and the density is constant. So we considered in our first example this idea of a convergent flow. So fluid flowing from left to right, from a large section to a small section. As long as the boundaries of the pipe are smooth, friction losses and energy dissipation are small, and hence the approximations made by Bernoulli are valid. Okay, so what we've done up until now is correct. Okay, so if we now consider a divergent pipe, we see this scenario. So our fluid is flowing from position 1 to position 2 to position 3. From position 1 to position 2, that's exactly what we talked about earlier. We see a drop in pressure. Our potential energy is the same. Z1 is the same as Z2 is the same as Z3 actually. Okay, so we can neglect the potential energy. So let's just consider pressure and kinetic energy. So from position 1 to position 2, if we've got 0 losses due to the fact that we've got smooth edges, we've got streamlined flow, so we're not losing any energy due to the fact that our fluid is turbulent and therefore creating frictional losses and generating heat and that sort of thing. We can simply consider the pressure, the energy associated with the pressure, and the energy associated with the velocity, the kinetic energy. Clearly, conservation of mass is telling us from position 1 to position 2, our velocity must be increasing. If our velocity is increasing, our pressure must be decreasing, and we see that. Our pressure, shown by these taps or represented by these taps, pressure at position 1 is greater than the pressure at position 2. Now, from position 2 to position 3, we've got this divergent section. Now, as long as theta is small enough, we maintain laminar flow, we maintain streamlined flow. Okay, there again, there's 0 losses associated with our turbulent flow, the friction inside the fluid, which would generate heat. So we're assuming 0 losses there. So from position 2 to position 3, we've got an increase in cross-sectional area. Now, conservation of mass is telling us if we're seeing an increase in cross-sectional area, we must be seeing a decrease in velocity. If we're seeing a decrease in velocity, we must be seeing a decrease in the energy associated with the kinetic energy. If we're seeing a decrease in the energy associated with the kinetic energy, we must be seeing an increase in the energy associated with the pressure. So from position 2 to position 3, the pressure increases, and actually that's fully restored. The pressure is fully recovered. So the pressure at position 1, this height of fluid here, would be the same as the pressure at position 3, sorry. So the height of the fluid here would be the same as the height of the fluid here. If theta is small enough and we don't have any energy losses associated with turbulent flow and frictional losses and so on. Okay, so the velocity at position 1 would be the same as the velocity at position 3 if the area at position 1 was the same as the area at position 3. And if that was true, the pressure at position 1 would also be the same as the pressure at position 3. Okay, as it goes through this restriction here, it increases in velocity, decreases in pressure, and it comes out the other side here. And like I say, as long as theta is small enough, we see a decrease in the velocity, we must see an increase in the pressure. Okay, so our divergent tube works in exactly the same way as our convergent tube, as long as theta is small enough when we consider the energy changes of our fluid flowing through our pipe. Now, let's consider what happens if we haven't got this scenario where we maintain laminar flow, streamlined flow, due to the fact that we've got small theta. Let's consider something like this. We've got a backward facing step. We've got unstable turbulent flow here. Okay, now the unstable turbulent flow would result in shearing of the fluid, which would lead to heating of the fluid, which would lead to energy losses. Okay, so we can no longer say that the energy at position 1 is the same as the energy at position 3 because we've lost some energy here. Okay, so from 1 to 2, it would be exactly the same. Work, flow, the energy associated with the flow and the energy associated with the pressure is converted here to energy, an increase in the kinetic energy and therefore a decrease in the pressure. Okay, so from 1 to 2, exactly the same scenario as we saw previously. However, from position 2 to position 3, we've no longer got conservation of energy. We're losing some energy there. Okay, so from position 2 to position 3, we are seeing a decrease in kinetic energy. We're seeing an increase in cross-sectional area. And if the cross-sectional area at 1 is the same as the cross-sectional area at 3, then obviously the velocity at 3 would be the same as the velocity at 1. Okay, so we've got an increase. It maintains the same kinetic energy, but if we're seeing it maintains kinetic energy, we must be losing the energy associated with the pressure. Okay, so before we were seeing the energy here, we said it was the same as the energy here. However, what we're saying now is we've lost some of that energy. So the energy associated at position 1 is greater than the energy associated at position 3. So we can say this: P1 plus a half rho U1 squared is greater than P3 a half rho U3 squared. Okay, notice there's no terms there associated with the potential energy. We've removed those terms. Now, U1 is the same as U3. Okay, assuming the cross-sectional area of the pipes are the same, U1 is the same as U3, so therefore this term here, a half rho U1 squared, is equal to a half rho U3 squared. So those terms would cancel out. So therefore P1 must be greater than P3. P1 must be greater than P3. Okay, so P1 here, pressure here, is greater than the pressure here. So we see a reduction in pressure, and that reduction in pressure is equal to this energy loss. So we can see our pressure represented by this height of fluid. We've got our tap coming in here, this height of fluid here. We can see that is reduced at position 2. However, it is not recovered when we go to position 3 because we've lost some energy. Okay, so this pressure remains quite low here. Okay, so we've got a high pressure at position 1, we've got a lower pressure at position 3. Okay, there's a loss of static pressure due to the fact that we've got those energy losses. The other thing that we've assumed are zero energy losses associated with the wall of the structure. Again, if we think of our wall here, we've got our fluid flowing from left to right. If we've got a rough surface, if we've got small steps on that surface, that would lead to turbulence and recirculation, frictional losses just downstream of those rough surfaces. Okay, so those rough surfaces cause disturbance to the streamline flow. There's higher friction and energy losses. The amount of disturbances is dependent on the Reynolds number. Clearly, as our Reynolds number changes, that will determine whether or not our flow is laminar or turbulent. So it's good practice, instead of having these steps, to have nice smooth surfaces, nice large radii, to maintain laminar smooth flow. So therefore we don't lose any energy associated with this turbulent flow, which would lead to losses associated with heat transfer. So if we have a look at this first handout, we've talked about Bernoulli's equation, we've talked about our losses associated with any friction, for example. We've talked about this idea of a convergent horizontal pipe, and then we've talked about a pipe which is the same cross-sectional area and is increasing in height, so we're gaining potential energy. If we use all of that associated in conjunction with conservation of mass, we can answer these questions. If we look at the end of this handout, there's 5 examples there. What I would like you to do now is to have a go at those examples. I will upload some solutions to those examples. So if we look here, we've got some solutions to those examples. We've got our fluid flow. We've got details of how we would go about understanding the changes from position 1 to position 2, for example. We're considering Bernoulli, so therefore we can calculate the velocities, or change in velocities, or the change in pressures, or whatever it is that we're interested in. So have a go at those examples. We've got example 1, 3 to 5 there. You should be able to answer all of those based on what we've discussed today. and using Bernoulli's equation, like I say, in conjunction with conservation of mass, you should be able to answer those questions. So I'll upload those solutions to the Teams area. You can have a go at those examples, and then we will discuss those examples in class and discuss the concepts that we've talked about today and have a look at any issues that you've got regarding any of those questions. Okay, thank you. Until next time, I'll see you later. Cheers. Bye-bye.